So I will start with thanking the organizers for inviting me to give this presentation. And yes, so let me start. Yes, so before going into actual theory of what we do, I will start with just reminding key energy scales in these materials. So basically, if we look at the periodic table at transition metals and ask which is the ratio of relevant energy scales, then for 3D series, we have a situation where typically Hund's rule coupling will be stronger than crystal field. Hence, we have tendency towards high spin states, and spin orbit is rather small. So on result, we have as I said, high spin states and usually Jahn-Teller, large Jahn-Teller effects lifting orbital degeneracy. For 5D series, the situation is different. First, crystal field, due to large spatial extension of 5D orbitals, it dominates over Hund's rule. So typically, we have low spin states. And then spin orbit, of course, increases a lot as one goes towards 5D series. And in result of this, we have spin orbit entangled ground state multiplets. To understand more precisely how they appear, how this spin orbit entanglement works, so let me first concentrate on a single octahedron containing magnetic 5D transition metal ion. So as I said, crystal field splitting will be large. So if we are dealing with occupancy which is less than 6, then only T2G states will be filled. And there is a well-established approach to deal with spin orbit in this case. So one can introduce so-called pseudo-orbital angular momentum, L equal 1, which has the same matrix elements as the physical one within this T2G manifold, but with inverse sign. And in result, the third Hund's rule, which one has in atomic physics, it is reversed. So for less than half filled shell, the total angular momentum will be sum of pseudo-orbital and spin 1. And so then, starting from this, one can draw this kind of level diagrams. So for example, if one puts one d electron, so one adds to, so one has, of course, Hund's rule state maximizing the pseudo-orbital momentum and the spin. And so they will add up, giving us effective J3 half for the ground state. And if we go to D2, then we get, with the same arguments, the ground state having J equal to 2. And so this kind of ions and oxides and double perovskites formed with these ions, they can host these multipolar phases. So here I also add d equals 3. So as Bruce already discussed, this is a special case where there is no orbital moment and no spin orbit active within ground state multiplet. Anyhow, so the question is how these multipolar moments appear. And to understand this, one can start with rather standard superexchange models. So basically, one can consider hopping, for example, between two XY orbitals through neighboring oxygens. And what one derives is this kind of coupling, which is strong anti-ferro between spins of these orbitals and ferro between orbitals. And similar treatment can be applied for the case when we want to consider coupling between two orbitals which are orthogonal. In this case, coupling between spins is ferro and between orbitals is anti-ferro. So this kind of treatment was applied in this rather famous work of Chen-Pereira imbalance. So they also decided so that apart from this superexchange, what can be important is also classical electrostatic coupling between this kind of orbitals, because they have a large spatial extent, and so there can be large quadrupolar moments involved. Anyhow, once this kind of Hamiltonian is written in spin orbital space, one needs to take into account the fact that spin orbit is much larger than these superexchange energy scales. And hence one can project everything in the space of this J3 ground state. And what one sees after the projection that these operators, they map into not simply into angular momentum, let's say Jx, but also have a contribution of the product of three angular momentum, which is commonly called octupole. So one sees that spin in initial spin orbital manifold containing 6 states within J3 it transforms into some kind of combination of total angular momentum and octupole. And charge actually maps into square of angular momentum, which is quadrupole. So this is how naturally this projection onto the ground state leads to appearance of multipoles. So one can introduce this in a little bit more systematic fashion by just considering density matrix of a given J effective space. And it is known that this density matrix can be expanded into multipoles. This is multiple expansion of these four are actually the same operators which I showed before, but just normalized. On the right, I show the table of them. So typically, basically the largest rank of multipole we can have for a given J is equal to 2J. So for example, for J3 the maximum rank is equal to 3, which is octupole. And so these operators, they form similar to spherical harmonics, the basis of irreducible representation of rotation group. And another important point is that those which are even in K, it's obvious they are invariant under time reversal, but those which have odd K, they switch sign under the time reversal, so they represent magnetic density, and even K moments represent charge density. So they have two different types. And basing on this, we can immediately write the expected form of low energy Hamiltonian for a given effective J. So this will be written like that. So we have all a coupling between all possible multipoles which are allowed within the given J manifold. And this is a matrix of coupling constants. So as I said before, moments for odd K will correspond to magnetic degrees of freedom, and moments for even K will correspond to charge degrees of freedom. And they cannot couple because of time reversal symmetry. But otherwise, this V is a large general matrix, which for J3 is like 15 by 15. And for J equal to, one can easily calculate it's 24 by 24. And so this makes calculating of this matrix from ab initio is kind of complicated task as compared to the standard Heisenberg model. If we have a compound which is described by this model, one needs to know only one number, while here for each bond we need to know a rather large matrix. Okay, so how do we approach this problem? So we start with DFT plus DMFT, which I will not describe. I guess everyone is familiar with this. Only important point is that we don't really use the full DFT plus DMFT. We use a very simplified version of it, which is based on quasi-atomic approximation to the impurity problem. So basically, in the Bas-Green function, we cancel the actual hybridization function, and then the whole impurity problem boils down to diagonalizing of this quasi-atomic Hamiltonian, where one electron part consists of some uniform shift, spin orbit, and crystal field. So we already have crystal field embedded into our model in this DFT plus Hubbard 1. However, if you want to calculate ordering phenomena, we need to include superexchange or kinetic exchange, which is really driving force for the order in compounds like double Perovskites. And it's obvious that if we simply do like usual DFT approach when we run some broken symmetry phase and expect it to be stabilized, this will not happen with within DFT plus Hubbard 1. Since we canceled hybridization function, we simply don't have superexchange. So in our impurity problem, it will not feel exchange, let's say, kind of exchange field coming from other sides. We will never get a symmetry broken solution within DFT plus Hubbard 1. So then what we do is that we start with this paramagnetic electronic structure obtained with DFT plus Hubbard 1, and then consider small fluctuations. It's kind of post-processing treatment on top of Hubbard 1. And with this, one can actually derive this kind of low energy Hamiltonians. So to describe this in more detail, so here there are some formulas. So we start with the expression for ground potential within DFT, ground thermodynamical potential within DFT plus DMFT, and consider small fluctuations on two magnetic sides, which break initial symmetry of paramagnetic state. And then we calculate the response due to this, and this can be shown to result in this formula, where for matrix element of effective Hamiltonian connecting two shells which are in a certain ground state atomic configuration, one gets this formula for these matrix elements, which includes response of atomic self-energy to the appearance of this kind of symmetry breaking on one side, the same for the second side, and also one electron propagators connecting one side to another one and back. Okay, so once we calculated all these matrix elements for a given pair of atoms, then we can map these matrix elements into effective Hamiltonian with interacting multipolar operators, and that's what we do. And in result, what one gets is actually this kind of general effective Hamiltonian. So now I will turn to applications. I will more or less follow the order which was proposed by Bruce. So I will start with a relatively straightforward case of these double Perovskites. So as already was mentioned in the previous talk, these compounds are relatively less exotic. So the point is that we have Hund's rule state for Hall field T2G. We have only spin in this case within the ground state multiplet. The orbital moment is 0. And then the expected model would be just something like that if we forget about spin orbit coupling. So just Heisenberg model, which is gapless. So experimentally, as Bruce already presented, one finds indeed some not very exotic antiferromagnet with 001 propagation vector. And the real puzzle is an excitation spectra. Again, it was already presented. So the point is that one has very large spin gap, which is quite unexpected for the cubic case when one has no single line anisotropy for acting within J effective 3/2. And this gap seems to scale as a function of spin orbit. So in the osmium compound, so it's the compounds of the same type, but simply one can put as a 5D osmium or 4D ruthenium into it. And in the osmium compound, the gap is 17 millieV. In ruthenium, it is smaller. So the question is, what is the origin of the gap? So after doing a DFT plus Hubbard 1, I basically applied the technique which I just described to calculate the effective Hamiltonian. So again, it is in this form, and the coupling constant between two neighboring osmium sites connected by this lattice vector is a 15 by 15 matrix. So it's difficult to present just with numbers, hard to see anything. So I present it as this kind of color map where bright red color corresponds to strong anti-ferrocoupling and blue color corresponds to strong ferrocoupling. And what one sees that, of course, as expected, there is very strong anti-ferrocoupling between dipole moments. This is this square. So coupling moments of rank 1, which are simply dipoles on one side and on another side. But also what one finds is relatively strong dipole octopolar couplings. So they're still quite a bit smaller than the leading dipole ones, because those are multiplied here by 0.1 to make the rest visible. But they make almost 10% of Heisenberg terms. So one can write this kind of effective Hamiltonian for a given bond, including only these leading couplings. And what one sees that in result, Hamiltonian doesn't have continuous symmetry. These couplings, they have only, these octopoles, if one transforms them into cubic representations, they have only cubic symmetry. And couplings for different reducible representations within cubic symmetry for octopoles belonging to different reducible representations, they're distinct and they're not related by any symmetry. So the Hamiltonian has only cubic symmetry and not continuous one. Then one can solve this in mean field, and indeed, mainly due to the effect of this dipole octopolar couplings, one gets this kind of 2K structure, which is somewhat lower in energy than a longitudinal 1K structure, which is competing in our case. Okay, and then the next step is to calculate excitation spectra. We do it starting from mean field ground state, applying rather standard RPA technique to calculate dynamical susceptibility, and then from imaginary part of dynamical susceptibility, one can calculate Ines intensity. And this is the result, and indeed one finds a rather large clear gap in the osmium compound, and also a gap in the ruthenium compound, which is smaller. And this was compared with experiment, with measurements of Bruce and co-authors. So for example, this experimental spectra integrated over momentum is shown here by red dots, and calculated spectra for just integrating this over Q is shown here in blue. And one sees reasonably good agreement. And for the ruthenium compound also, there is a reasonably good agreement. It's actually results are quite sensitive to the value of J. Okay, so to demonstrate that the gap is induced by these terms, one can do it explicitly by multiplying these dipole octopolar terms in the Hamiltonian by some factor f, and then scaling this factor down, and one sees that the spin gap closes roughly as the square root of f. And okay, so moreover, one can understand appearance of these dipole octupolar terms from analytical considerations, just introducing this kind of simplified tight binding hopping model, similar to the one which I discussed for the case of superexchange. So there is strong hopping between orbitals line and plane for a given bond, which also belongs to this plane, and weak coupling of another side between two orbitals which are orthogonal to this plane. Then one can simplify Coulomb repulsion as well to be able to treat everything analytically. And then what one sees once spin orbit is introduced, there is a splitting of levels, and then there is a mixture due to spin orbit of some these excited levels into the ground state. And then one can calculate matrix elements of superexchange with this wave function. And what one finds that, of course, if spin orbit is 0, then one finds pure Heisenberg model. And the next order, which is basically square in spin orbit coupling strengths. So this kind of strong diagonal hopping contributes only to dipole-dipole and dipole-octupole. And dipole and quadrupole is contributed in the same order, but only these terms, T prime term contributes into quadrupole, hence it's weaker by this factor. So this explains why it's dipole-octupole and not quadrupole, which causes the gap. Okay. So now I'm turning to another set of materials, also presented by Bruce. So this is a very unusual case where one sees phase transition, very clear phase transition, and one sees appearance in muon scattering experiments of some magnetic density, but there is no Oderet moment. So no dipole Oderet moment. So I will not again describe experiments that were already described. I will just mention that for this hidden order, there were, of course, some theories which were based on some estimates for relevant energy scales. This was described by Bruce, that basically if we suppose that there is a strong crystal field splitting within this J equal to ground state, then there are only quadrupole and octupole phases which can compete with each other. And there are papers favoring both of these pictures. So the aim of the study I'm going to present was to understand if we treat all these degrees of freedom in the same way and in an unbiased way. So the question is, which order will we find? So again, using DFT plus Hubbard 1, here I mentioned some calculation on details. So we use Win2K and tricks implementation of DFT plus DMFT and some Hubbard 1 solver. What one finds is indeed there is a splitting of J effective to ground state, and crystal field splitting is found to be around 20 millieV and agrees with experimental estimate. But then the next step was to calculate all these intersite exchange interactions, which I show here in the same form as for the previous case. I exclude K equal 4, so-called hexadecapoles. For them, coupling is really small. So relevant couplings are between dipoles, quadrupoles, and octupoles. So one sees there are a lot of matrix elements, but their magnitude is at most 3 millieV. So if one compares this with crystal field splitting, that obvious that only those which can act within this EG doublet will be relevant. So these are these couplings which are highlighted here. So one can put them in this kind of pseudo-spin 1/2 model, but physically they are different. So tau z is and tau x are quadrupoles, and tau y is this xyz octupole. And so what one sees if one analyzes ab initio calculated couplings, that coupling between octupoles is larger and also it is fairer, while couplings between quadrupoles are smaller and antiferro. And hence, we deal with magnetic, with FCC lattice of magnetic ions, which is frustrated with respect to antiferromagnetism. So, of course, ferrocoupling will be more favored by this lattice, and also it is larger in magnitude. So again, one can solve this model in mean field. It's very difficult to do anything better than mean field. And what one finds is, indeed, if one looks at transition temperatures found in mean field, they are for the three compounds, they are roughly twice larger than experimental one, but they follow the same trend. And the competing phase, which one can obtain by setting to zero this leading octopolar coupling, it also appears. This is antiferro quadrupolar phase, but it has approximately 3 times smaller transition temperature and 3 times smaller ordering energy. So these calculations predict that ferro-octopolar phase, which is sketched here, will basically be the actual order in these compounds. Of course, there is a question whether electron-lattice effects will be important for these compounds, because quadrupoles can couple to the lattice, and this can lower again the energy of this antiferro quadrupolar order, and this we didn't verify. So now I'm turning to the last set of materials I'm going to discuss, and exactly I'm turning to the question how we can consider together superexchange and electron lattice within the same framework. So here I will focus on D1 double Perovskites of rhenium, which were again presented by Bruce before. But for this material, there is quite a bit of controversy regarding the magnetic structure. As was mentioned by Bruce. Anyhow, for one of these compounds, which is the most investigated, barium-2 magnesium rhenium 6 BMRO, one can clearly observe two-phase transitions. One at higher temperature doesn't correspond to any magnetic order, but some tiny lattice distortions were observed, and they were assigned to this kind of antiferro quadrupolar order of x square minus y square quadrupoles. And there is another component which is much weaker, which is ferro quadrupolar z square. So this is combined order, which one finds between 33 and 18 kelvins. And below 18 kelvins, the system orders into this kind of counted antiferro structure. Okay, in accordance with this paper, anyhow. And then the same group basically studied BMRO under pressure and found that as pressure applied, as the pressure increases, quadrupolar order is suppressed. And there is only content antiferro becomes just collinear antiferromagnetic phase. And there is a bunch of compounds, as also discussed by Bruce. Some of them show like zinc and cadmium two-phase transitions. They're similar to BMRO. And calcium, for example, shows only a single magnetic phase transition. Okay, again, starting from standard superexchange models, which include this classical quadrupolar electrostatic coupling, which we, by the way, neglect. So this is an open question whether it's really important, but we didn't estimate it. So basically one can reproduce pretty well this experimental result. Actually, it's not a it's actually prediction. This chain balance paper was published quite many years ago before the actual experiments were done. And for certain set of parameters, one indeed finds first transition to antiferric quadrupolar phase, and then at lower temperature transition to counted antiferromagnetic phase. And so this kind of picture stemming from this paper is used a lot in interpreting, kind of making sense of experimental data, but it's sometimes a bit difficult because, for example, one could say, okay, as one decreases unit cell volume, one also increases quadrupolar classical electrostatic coupling, and in result one would have a tendency towards quadrupolar phase. Yeah, but in reality, quadrupolar phase is also suppressed by pressure. So it's not very clear. It's a extension of the volume suppresses quadrupolar phase, and compression of the volume, as in pressure experiments done in BMRO, also suppresses it. So it's not very clear whether this unit cell volume parameter is really relevant. And there is completely another way of thinking about these compounds, which is based on electron-lattice coupling, which was neglected before in superexchange models. So D1 ground state, J 3/2 multiplet, it is Jahn-Teller active, meaning that there will be this linear term coupling the quadrupole with the corresponding lattice distortion of the same symmetry. And these lattice distortions will couple through the lattice through usual elastic interaction. And so Ivahar and Chibataro, this is their paper, they calculated, they considered this kind of model, and basically they assumed that all difference between compounds are within this term, which is the elastic coupling. And they also consider that they are in so-called strong Jahn-Teller regime, meaning that basically system is always distorted. So basically you have some kind of fluctuations above transition temperature of between different distorted configurations. So you have either basically compression of octahedron along X, along Y, or along Z, and so octahedron fluctuates between these different configurations. So anyhow,
Leonid, you should conclude in about a couple of minutes so that we have time for questions.
Okay. Okay, fine. So basically they consider this and they found that they can also explain experimental data with this. So our calculation, so we did the same kind of calculations for superexchange, and we found that superexchange alone doesn't explain these results, appearance of this antiferric quadrupolar order, because real competing ferric quadrupolar interactions which are stronger and would favor a ferroic quadrupolar order. So basically what we did, we added electron-lattice coupling. So we calculated Jahn-Teller coupling, we calculated elastic intersite coupling. And in result, what one has is this kind of Hamiltonian, I think I was shown here, which combines all these three terms. This can be solved. I have no time to explain how to do it, but basically with this we find indeed transitions which agree and phases which agree with experiments, so antiferro quadrupolar, and then counted antiferro phase with the net magnetization along 110. And we also find that basically change of volume affects very little the phase diagram. In contrast, if one applies a little strain, and in pressure experiments, the pressure medium was not completely hydrostatic, so there were some strains. These strains suppresses very easily this antiferric quadrupolar order. So actually, our prediction is the whole effect is not in the effect of pressure is not in pressure itself, but in inducing some strains in the compound, which destroys antiferric quadrupolar order. Okay, so I would just acknowledge my co-authors. First of all, Dario Fiore-Mosca, which was Polytechnic, which was a postdoc in our group for 2 years, and who worked a lot on these D1 systems. And then Cesare Francini, with whom I collaborated very fruitfully for several years. And also we had collaboration with theoretical group at Zurich, and this experimental group at EPFL Lausanne. And these are my conclusions. So thank you very much for your attention.
Thank you very much, Leonid. Beautiful talk. There is time for questions. Well, if nobody wants to go first, I'll maybe Bruce, you have.
Yes. I was trying to figure out how to put my hand up and couldn't figure it out. Anyway, so this last point that you were making about the sensitivity to strains as opposed to pressure, I was just wondering if that would, if there's any unusual effects that would be expected from quenched impurities, which may locally strain a given area, and if that had been considered at all, or if you thought there was anything interesting with the influence of...
In D1 or in D2, in which systems?
Well, say you were talking about this in the context of D1, but
Yes.
actually in the context of any of them, for that matter.
Yeah, in the context of, in a sense, I think if these are local impurities, they shouldn't affect the phase stability, no? So maybe will be something around them, but otherwise the phase shouldn't be affected unless there are a lot of them.
Mm-hmm.
Right? So this way, the strain is still, it's kind of smallish, but it's not so small. It's like 0.2%, something like that, right? So wow, I think it will be difficult to affect really strongly the phase stability with just impurities. I think this question was also considered for the case of D2, whether one can, by adding some impurities, whether one can suppress the octupolar phase. This we didn't consider, yeah. But for D1, I think more important in this case is the strain, which appears not only due to pressure experiments, but also some compounds like calcium compound, they're just naturally strained because of not perfect cubic structure because of the lattice. And this can explain why in calcium one doesn't see this quadrupolar phase, because it is suppressed by the strain, by the purely lattice strain.
Okay, thank you.
Okay, next question by Alberto.
Hello. I wanted to ask, so you mentioned that all of these results are reliant on the Hubbard-1, so quasi-atomic approximation of the treatment of the interaction. I was just wondering on what do you expect of this physics is maintained if if this approximation is relaxed. So like if we were like to consider situations where the bandwidth is larger, do we expect these effects to be washed out, or do we expect them to be still present, or like what should change in your opinion?
Well, I guess if you approach to, let's say, more transition point, you should have high order contributions to superexchange, like not T square, but T4 and so on. It's difficult to say how they affect the result. So I'm considering a situation where you're still in the insulating phase, but the gap gets smaller, and you have all these other contributions. I don't think they will necessarily suppress multipolar order. It's difficult to say. Anyhow, it's possible maybe to extend this approach to include these high rank contributions. We didn't do it at the moment.
Thank you.
Antoine?
Yes, I just wanted to make sure I understand the current situation with the D2 case, the case where there is some hidden form of order. So can you summarize what is understood and not understood in comparison to experiments on this case?
Okay, so D2 basically is the fact that there is this ferroctopolar phase explains the absence of detectable lattice distortions and presence of magnetic density, which is detected by muon scattering. At the same time, we still have a problem. I didn't show these slides because of the lack of time. But basically, experimentally, as Bruce shown, one sees an additional peak appearing in the excitation spectra when below the transition point. And this we tried to reproduce based on ferroctopolar phase, and we couldn't. Basically, the point is that this excitation exists, but it wouldn't be seen in an elastic neutron scattering because of extinction of matrix elements relating ground state and this, let's say, exchange feature.
I
And
see.
so the only way how we could reproduce it is by introducing some small distortion. So when we distort it, then this extension, this condition of zero matrix element, it is basically violated, and then we have this exchange feature appearing. Since they don't detect this distortion, actually, in accordance with our calculations, this distortion can be quite small. But still, they don't see it. So it's possible that there is some kind of dynamic Jahn-Teller effect, which still exists in this phase and which produces this feature. But this needs to be actually, of course, calculated. And another point, of course, one for the quadrupolar phase, quadrupolar order parameters, they are Jahn-Teller active. And we didn't include electron-lattice coupling yet. It's not clear whether octopolar phase will be still stable when quadrupolar phase is stabilized in addition by electron-lattice coupling. This needs to be understood.
Okay, thank you very much.
Adam?
Hi, thanks for the talk. My question, I was curious about your study of electron-lattice coupling in BM-Rho. My question is, when determining the coupling from ab initio, I think I saw that, yeah, you do DFT plus Hubbard 1 calculations of the structure distorted by relevant modes. My curiosity is how much those Jahn-Teller couplings change when you do, say, pure DFT versus DFT plus Hubbard 1. Like, is there a significant difference?
Well, I think so. We calculated it from DFT plus Hubbard 1, but in other work, which I also mentioned here, this one, so it all. So our collaborators, Max Merkley, Claude Ederer, they calculated it from DFT. So from DFT plus Hubbard 1, it's very easy to get them because basically you just look already at the splitting of relevant J3 half, and you can get directly this coupling constant already for J3 half ground state. In DFT, it's a little bit more complicated procedure because you don't see actual atomic states. But anyhow, they got something quite similar somehow. Yeah, I think they extracted it from density matrix. So they looked at the change of density matrix as they applied distortion, and there is a way, I don't remember the details, to extract Jahn-Teller coupling from this. And we had a good agreement between the two approaches.
Okay, great. Thank you.
Okay, I think our time is up.
Okay.
So thank you very much for very complimentary talks. Olivier, you may want to already announce the next speakers for December 16.
Yes. So we will have Herbert Fotso from the University of Buffalo. And the second speaker will be Yuta Murakami from Japan.
And so this will be a session devoted to out of equilibrium time-dependent things and probe, etc.
Yeah.
Okay, thank you, everybody. And thanks for the great talks.